In this unit, we introduce about the evolutionary computation, that is genetic algorithm. The outline of these lectures include introduction and simulation of the natural evolution, and we introduce about the genetic algorithm and case study about the maintenance of scheduling using genetic algorithm. And we finally make summary, and we have a homework for discussing. Can evolutionary be intelligent? Intelligence can be defined as the capability of a system to adapt its behavior to ever-changing environment. According to Alan Turing, the form or appearance of a system is irrelevant to its intelligence. So evolution computation simulated the evolution on a computer. The result of such a simulation is a series of optimization algorithms, usually based on simple set of rules. Optimization iteratively improve the quality of the solution until an optimal or at least feasible solution is found. So evolutionary usually is repeatedly to computation that based on some update operation that select the optima. The behavior of the individual organism is an inductive inference about how yet unknown aspect of its environment. If over successful generation the organism survives, we can say that this organism is capable of learning to period change in its environment. That means maybe the animal or people that he fit the environment, so they can learn the change of the environment. So the evolutionary approach is based on the computational model of natural selection and genetics. We call them evolutionary computing, an umbrella term that combine have a genetic algorithm, evolution strategy, or genetic programming. Umbrella term means that in this field, how many methods are included. In fact, many algorithms also the evolutionary computation. Simulation of a natural evolutionary that on July 1, 1858, that Carroll present his story of the evolution before Limna Society of London. This day marked the beginning of revolutionary in biology. So the Jones class story of the evolution, together with the Westerman's theory of the natural selection and Mendel concept of genetics, that grow reference non Jordan pattern. So the most general, the evolutionary is based on the Neo-Darwinism, that is based on the process of reproduction, mutation, computation, and selection. The power to reproduce appears to be an essential property of life. The power to mutate is also guaranteed in any living organism that reproduces itself in a continuously changed environment. Process of the computation and selection normally take place in natural world, where expanding population of different species are limited by a finite space. So the evolution can be seen as a process leading to the maintenance of population ability to survive that reproduce in a specific environment. This ability we say the evolutionary fitness. So the evolutionary fitness can be also viewed as a measure of the organism's ability to anticipate change in its environment. So usually the fitness is good. That means that he can live in the environment is better. So the fitness or the quantitative measure of the ability predict environment change and response at the quality that can be considered as the quality that it is optimized in a natural life. So how is a population with increased fitness generated? So let us consider a population of the rabbit. Some rabbits running very fast than the others. And we may say that this kind of the rabbit process is super fitness because they live a great change of avoid force, surviving and then breeding. So means that the rabbit he can run very quickly, so the fox cannot catch him. So he can live and breeding his children and for his generations. So if two parents have a super fitness, there is a good chance that a combination of their genes will produce an offspring with even higher fitness. Over time, the entire population of rabbits became fast to meet their environment change in the face of the fourth. So all methods of evolutionary computing simulate a natural environment by creating a population of individuals evaluating their fitness, generating a new population through genetic operations, and repeat this process a number of times. We will start with the genetic algorithm as the most of the other evolutionary algorithms can be viewed as variation of genetic algorithm. Genetic algorithm is in early 1970s. That is John Holland introduced the concept of the genetic algorithm. His aim was make the computer to do nature. Holland was concerned with the algorithm that manipulate string of binary digits. Each artificial chromosomes consists of a number of genes, and each gene is represented by 0 or 1. So the genes combination became a chromosome. Nature has ability to adapt and learn without being told what to do. In other words, nature finds good chromosome blindly. Genetic algorithms do the same. Two mechanisms link a genetic algorithm to the problem it is solving in coding and evaluation. So we use a genetic algorithm. The first thing we need to do is encoding our problem. That we mapping our problem to the chromosome, and then we operation on the chromosome to evaluation the result. Genetic algorithms use a measure of fitness of individual chromosomes to carry out reproduction. As reproduction takes place, the crossover operator exchanges part of two single chromosomes, and mutation operation change the gene value in some randomly chosen location of the chromosome. So here introduced is two operations. One is crossover operation, and the other is use the mutation operation. This is the most important part of the genetic algorithm. The basic genetic algorithm step, we can find that step 1 represents the problem variable domain as a chromosome. Usually is a fixed length. Choose the size of chromosome population n. This means that we generate the number of the n chromosomes. So your problem can have many chromosomes. The crossover probability set up a PC, and the mutation probability set as PM. So these two values we also set up in advance. PC value usually is greater than PM, and PM usually a small one. The next step, we need to define a fitness function that used to measure the performance or fitness or an individual chromosome in the problem domain. This fitness function established the basis for selecting chromosomes that will be made during reproduction. Step 3. Randomly generate an individual population of chromosomes of the size n. So here means we have a number of n chromosomes. Each chromosome is S1. The step 4, calculate the fitness of each individual chromosome. So the chromosome will be put into a function. This function is to calculate the fitness. And so each chromosome have a fitness value. Then we can select which one can be to generate their generations. Step 5, select a pair of chromosomes for mating from current population. Parent chromosomes are selected with a probability relative their fitness. Step 6, create a pair of offspring chromosomes by applying the genetic operators, crossover and mutations. And then go to step 7. We place the created offspring chromosomes in the new population. Here, the offspring means his children of the current chromosome. And step 8, repeat step 5. What is step 5? So we repeat to generate the mate of the chromosome, and then run step 6 and step 7 until the size of new chromosome population became equal to the size of the initial population. This means that initial population we have n chromosome. So after the processing, their offspring still have the number of the n populations. Step 9, replace the initial chromosome population with the new population. The new population is offspring. And step 10, go to step 4 and repeat the process until the termination criterion is satisfied. Genetic algorithms. GA represents an iterative process. Each iteration is called a generation. A typical number of generations for a simple genetic algorithm can be ranged from 50 to over 500. The entire set of generations is called a run. Because genetic algorithms use a stochastic search method, the fitness of the population may be remain stable for a number of generations before a super chromosome appears. A common practice is to terminate a genetic algorithm after a specified number of generations, and then examine the best chromosome in the population. If no satisfied solution is found, then the genetic algorithm is restarted. So this is repeatedly to run. And in general, we run 50 to 500. So every time we run all the chromosomes, we set a run. A run, we also set the actual, EPO CH. Okay, this is an example of genetic algorithm case study. A simple example will help us to understand how a genetic algorithm works. Let us find the maximum value of a function 15s minus s squared, where the parameter s value range is between 0 to 15. For simplicity, we may assume that s takes only integer value. Such chromosome can be built with only 4 genes. That why select 4 genes to build? Because that from 0 to 15 we can use binary code to encoding it. For example, the integer 1, that the binary code is this one, 0001. Why the 0001? Because this is based on 2 order 0, 2 order 1, 2 order 2, and order 3. So we can decode the binary code to map into integer. We also can from the integer to encoding became binary code. 4 is 0 at 4 at 0 at 0. Oh, that is mapping to 4. I think this is very basic for the binary operations. Suppose that the size of the chromosome population, that the number n is 6. 6 means we randomly generate the 6 chromosome. That the crossover probability is set to the 0.7 and mutation probability is set to 0.001. This function, fitness function in our example, is defined by fs equal to 15s minus s squared. So from here and real example, because the initialize the chromosome is 6 chromosome from S1 to S6. So we randomly select the chromosome. This is randomly selection from the pool of the 15 from 1 to 15. And then this chromosome can be decoded to the decimal value. And then we try to find the chromosome fitness. How we find the chromosome fitness? For example, this is 12. 12 because our function is like 15s minus s squared. So 15s minus s squared. We use a simple example. For example, s is 1. 1 replace here. 15 minus 1. 1 square is 1. So the result is 14. So we can find the 14. The same method we can find the chromosome fitness. That is that when the chromosome decoder is 12, then the chromosome fitness is the 36, and so on. And then we try to find this is the fitness value. We try to find the ratio of the fitness. Why we need to find the ratio? That is used to select their offspring that from here. But it's better we have a ratio that we can use here to rotate and randomly to select. So here we can find the chromosome initialized location because we have this 6 point. This 6 point is located this 6 location. This curve is the function curve. Our chromosome, the best solution is located here because here the value is maxima. So in natural selection, only the fitness species can be survivor breed, thereby passing their genes on to next generation. Genetic algorithms use a similar approach, but unlike nature, the size of the chromosome population remains unchanged from one generation to the next. The last column in table shows the ratio of the individual chromosome fitness to population total fitness. So that means the value, how we get the value. The value here is from summation and the ratio. For example, we find this one, we use this one. This one is 36 divided by 36. Then we summation 4 and summarize 14. 14 has 2 and 14 and summarize 16. Why 56 and summarize 54 together. So this is the ratio. We find this ratio. Okay? So the last column in table shows the ratio of individual chromosome fitness to the population total fitness. This ratio determines the chromosome change. Change is the probability of being selected for mating. The chromosome average fitness improves from one generation to next generation. So we can use the row here idea to do the selection. The most company use chromosome selection technique. We said the row here selection. Row here sometimes in Chinese we say the 俄罗斯轮盘. That is Russia here set, here wrote. So we have a ratio like this. That is based on previous. If we rotate the here, then the index we are indicated to one of the 6 location because some regions are bigger. For example, the big one is S5. This one is the big one. The second is S6. S6 is black. And the third is S2. S2 is here. So when the here rotate, the probability of select S5 is highest. And then second is the S6. And third is the S2. The next probability is S3 and S4. So when we have a next generation, more probability will select the bigger fitness. That means the fitness value is better that they select to generate their upstream probability is higher. So in our example, we have an initial population of 6 chromosomes, such to establish the same population in next generation. The row here would be spun 6 times. Once a pair of parents' chromosomes is selected, the crossover operator is applied. So the first is to the crossover operator. First, the crossover operator randomly chooses a crossover point where two parents' chromosomes break, and then exchange the chromosome part after that point. As a result, two new offspring are generated. If a pair of chromosomes doesn't cross over, then chromosome cloning takes place, and the offspring are created an exact copy of each parent. So we can find the example of the chromosome operation. For example, the first one we select is S6 and S2, where the I is the number of the rung, or number of the rung. For example, the first generation rung, or I is 1. And then we select a close point, or close point. Here is select this location, this location. And then we do the crossover. The crossover means we move based on this cross point. We move these two values. The point right side two value is changed with other chromosome right side two value, and then generate a new one. So this new one is 1 0 0 0, and this new one is 1 0 1 0 1. If the cross point select is here, or select is here, then its change is 3 bit, the 3 bit. That is became 1 1 1 1, and this one became 0 1 0 0. Okay, so this is the operation about the crossover. So that look the next operation, mutation. Mutation represents a change in the gene. Mutation is the background operator. Its role is to provide a guarantee that the search algorithm is not trapped on a local optima. Trap means that for example, we said the track or the converse graphic. The track means that his location usually here. The track means the location he rotated is here. We use other colors to show more clear. And we use this color. So this means that they usually run in here. So that is a trap. The mutation hope to jump this trap. Maybe he jumped to this location. Because they will to find the raw value. So they run here. The mutation operation that hope to do is to jump. Hope to do the jump operation. So the mutation operation flip a random select gene to a chromosome. The mutation probability is quite small in nature and keep low for genetic algorithm, typically in the range between the probability is 0.001 and to 0.01. So that is a small one compared with crossover. So this is an example of the mutation. The mutation first step we need to select which bit need to do the mutation. Mutation means the change because here is 1. After mutation we change to 0. And here is 0. After mutation we change to 1. This is the operation of the mutation. So we summarize the problem of the genetic algorithm, how to solve this function. The first step is here. Randomly generation 6 chromosomes, and then we calculate the fitness and use the row here to select the mate, and then mate to do the crossover. And sometimes we select the probability is not to do the mating, then they keep the same. And then after the mutation operation, we got this one. And then after this, we got a new chromosome. So the new chromosome is like this. Then this chromosome, this 6 chromosome will replace the original one. And then this is finish a run and repeatedly to do the work. This is the operation of the genetic algorithm.